Thank you, Nima, for the invitation to speak at this very interesting event. The title of my talk is The Shapes of Spaces and the Nuclear Force. And this is the outline. We'll talk a little bit about physical mathematics, and then we'll talk about a problem in mathematics, then a problem in physics, and then the relations between them, and then we'll summarize. So, physical mathematics. What is physical mathematics? Well, it's a noun. That's how it's pronounced. And the definition is that physical mathematics is a fusion of mathematical and physical ideas which are motivated by the dual but equally central goals of elucidating the laws of nature at their most fundamental level, together with discovering deep mathematical truths. Now, that's quite a mouthful, so let me recap some of what you just heard from Graham and Natalie and Freeman and Karen with a quasi-historical explication. So I've always been fascinated that if you think about the founders of the modern scientific era, then if you ask, are they mathematicians or physicists, they would have said neither. They would have said they were natural philosophers, as Graham was explaining. And they were both, they were natural philosophers. There was no real separation. So after all, Newton and Leibniz invented the mathematical subject of calculus to solve physical problems about motion. Now today in the universities, we don't have departments of natural philosophy. We have departments of mathematics and we have departments of physics, and they often don't even talk to each other. So we could ask, when did natural philosophers become either physicists or mathematicians? And even around the turn of the 19th century, great figures like Euler and Lagrange and Gauss, these were again natural philosophers. So the separation really seems to be a result of specialization and the growth of science in the 19th century. And as described in Graham Farmilo's book, and we just heard about in the conversation, in the mid-20th century there was a long divorce between fundamental physics and modern mathematics, which started to change in the late 60s and early 70s, when some great mathematicians got interested in aspects of fundamental physics, and some great physicists started producing results requiring ever-increasing mathematical sophistication. So that in the past few decades, a new field has really emerged with its own distinctive character, its own aims and values, and its own standards of proof. And one of the guiding principles is certainly the discovery of the ultimate foundations of physics. And that quest has indeed led to ever more sophisticated mathematics. But a second guiding principle is that physical insights can lead to surprising new results in mathematics. And such insights are a great success. They are just as profound and notable as an experimental confirmation of a theoretical prediction. So today, I'm going to explain just one emblematic example, one story within the broader subject of physical mathematics about a remarkable convergence of physical and mathematical ideas. Now, this is a story in which I played a role, not a starring role. Two of the people who played a starring role are in the audience. A third is in Israel. And unfortunately, one of the major stars is no longer with us. So Michael Atiyah, in addition to being one of the greatest mathematicians of the 20th century, was also one of the most charismatic. And you could not talk to him without, he was just bubbling over with enthusiasm, with ideas. He was cheerful, witty, and extremely generous, and we're going to miss him a lot. So I'm going to talk about two basic questions, one in mathematics and one in physics. So in mathematics, the question is, what is the shape of a space? How can we tell when two geometric objects can be deformed into each other? And in physics, the question is, what holds stuff together? How can we describe forces that attract and repel matter? Now, at first, these two questions seem like they have nothing to do with each other, but I hope that by the end of the talk, you'll appreciate that they're actually deeply related. So let's begin with the mathematical question. So what is the shape of a space? So what do I mean by that? I'm talking about a subject called topology. So take a geometrical object. I'll call a geometrical object a space, and I'm not going to give it a very precise definition. For the experts out there, I'm talking about a compact Hausdorff manifold. But it's just a space, like the surface of a coffee cup. So take a surface of a coffee cup and imagine that this coffee cup is made of malleable material. So you can deform it continuously. You can squish, pull, push, but you're not allowed to cut, rip, or tear. In that case, you can take this coffee cup, and as this movie shows, you can continuously deform it into other shapes, like the surface of a donut. So in topology, the surface of a coffee cup and the surface of the donut are considered to be the same. So now suppose we have two different spaces, like the surface of a coffee cup, of a donut, and of a basketball. And we ask, how can we tell, are these topologically the same or not? What we need to find is a property that does not change under deformation. Such a thing is called a topological invariant. One such property is called the dimension of a space. So let's make sure we're all on the same page about what it means to talk about a dimension. So the screen here is a two-dimensional object. Why? Because you look at a point on the screen, and there are two independent kinds of motion. We can go down and up. Well, up is the opposite of down, so that's one kind of motion. Or we can go right and then left, and left is the opposite of right. So that's a second kind of motion. So when we talk about the position of a point on the screen, we need two real numbers, x and y, and that's why it's called two dimensions. Now, we live in three dimensions. You should imagine that x-axis is forward and backwards coming out of the screen. You could imagine living in a space with two dimensions, and that goes back to the beloved book called Flatland by Edwin Abbott, in which he imagines, or it's told, from the point of view of a square, which is confined to live in a two-dimensional space, like the surface of this screen. And in the course of the book, the square meets beings from a one-dimensional world. They're only allowed to go left and right, so they're beings from line land, and they start comparing notes and find interesting things. So in that spirit, let's consider topology in different dimensions. So let's start with one dimension. So there's a one-dimensional object, and we can deform it, and it's still one-dimensional. It can get very complicated, like the path in a labyrinth or some RNA, but it's still one-dimensional. Topologically, they're all the same. Now, something which is topologically different is a circle. Again, we can deform that. These two are topologically equivalent, but they're not the same as the line segment. So a topological invariant, so how do we distinguish these? So we need a topological invariant. So a topological invariant is the answer, I'll call it A of S, to a question you ask of a space S. And if S1 and S2 are two spaces and can be deformed into each other, that is, if they are topologically equivalent, then the answers are the same. So what's an example of a one-dimensional topological invariant? Well, here's the question. You take a little walk, and you get back home, and you always walk forward. And if the answer is yes, then topologically you have a circle, and if the answer is no, topologically you have a line. Now, this is a very good question. It gives you an example of what's called a complete topological invariant. So again, a topological invariant is a question so that if S1 can be deformed to S2, then the answers are the same. Now, dimension is an example of a topological invariant, but it's not good enough because we saw that the circle and the line are both one-dimensional, but they're not topologically equivalent. A complete topological invariant is a question that's so good that if the answers are the same, then S1 can be deformed to S2. So now let's talk about two dimensions. So what kind of two-dimensional objects can we imagine? Well, there's the surface of a basketball, and there's the surface of a donut, and it should be intuitively clear that these are topologically inequivalent. What else can we do? Well, we can put more holes in the donut, so we could have a two-hole donut or a three-hole donut, and so on. So how do we measure that topology? Well, a theme here is going to be you can measure topology by counting something. So you measure by counting holes, for example. But there's more than one way to count. If you imagine water flowing on the surface of a two-dimensional geometrical object, then because of the topology, there have to be drains and spigots. There have to be sources and sinks for the water. And if you count, adding with plus and minus signs, the drains and the spigots, you also get a topological invariant. Now, actually, these turn out to be related to each other. They're not independent topological invariants. There's a theorem in mathematics that says that that sum over drains and spigots is 2 minus 2 times the number of holes. So we'll see at the end of the talk, I'll talk again about two different topological invariants of four-dimensional spaces, and the relation between them will be extremely non-trivial. So here's just an illustration of that theorem. Imagine water flowing on the surface of a sphere. So there's a spigot here and a drain at the other pole, and they both contribute plus 1. So you add up the drains and spigots, you get 2, and that's indeed equal to 2 minus 2 times the number of holes. Here again is water flowing on the surface of a donut. There aren't any drains or spigots, so you get 0, and indeed 0 is 2 minus 2 times the number of holes. And here is a two-holed surface. And if you're not distracted by other things, you might want to calculate its topology. And the authors of this figure have imagined water flowing on this surface. And you sum over the drains and spigots. And this shows you the importance of the minus signs, because 2 minus 2 times the number of holes is minus 2. Now, before I go on, I want to talk about how you can make new topological spaces from old topological spaces by a process called identification or gluing. So you see, this talk is run on a shoestring. This is a one-dimensional object. And now what I'm going to do is I'm going to glue together the ends. I'm going to mathematically identify the 2 points. And now I have the new topological space, the circle. So you can make new topological spaces by gluing together points. So we could do that in 2 dimensions as well. So if we identify the opposite sides on a sheet of paper with the orange arrows here, we get a cylinder. And then if we glue or identify the green sides, we get the surface of a donut. Now we can do that in 3 dimensions as well. Imagine, now here your imagination, you have to use your imagination. So imagine that you're gluing the opposite sides of this cube. Then what you'll get is a space without any boundary. And why is that? Well, imagine that you're trying to walk through this golden arch here. Well, because of the identification, that golden arch is the same as this one. So if you leave, you come back in. So it's like the Hotel California. You can check out, but you can never leave. And for the same reason, you can also see the back of your head. So if you imagine standing under the arch and facing in, then the light rays from the back of your head come in through the other side, go into your eyes, and you see the back of your head. So clearly things are getting much harder. For example, if you take a 12-sided figure like this and identify opposite sides, again, you'll get a space with no boundary, and this is what it would look like to be inside one of those spaces. So clearly things are getting hard. You might think it's hopeless to go to higher dimensions like 4. Well, let's just agree that it makes mathematical sense. It makes mathematical sense because you can just specify 2 dimensions by the points x and y on the screen, 3 dimensions by x, y, and z. 4 dimensions, well, you just give it the address of a point has 4 numbers. Now there's, fortunately, a special kind of animal that has the ability to think clearly about these higher dimensional spaces and the topology of these higher dimensional spaces. And this animal is called Homo sapiens topologensis. And this animal can find topological invariants of higher dimensional spaces. So you might expect that as the number of dimensions increases, the problem gets ever harder. But there's a big surprise. For some questions, 4 dimensions is the hardest dimension of all. There are many unanswered questions about 4-dimensional spaces. And one thing we know for sure is that the world of 4-dimensional spaces is really wild. There's nothing even close to a complete topological invariant. So mathematicians that work on this subject write papers with titles like, will we ever classify four manifolds? A four manifold is a four-dimensional space. So now let's turn to physics. So in physics, remember, the question was, what holds stuff together? How can we describe the forces that attract and repel matter? So let's just remember, what forces do we know about? Well, we all know about gravity, and we all know about electricity and magnetism. And just based on your knowledge of electricity and what you were taught in high school science class about the structure of the atom, you can deduce the existence of another force, the nuclear force. You see, because here in the nucleus of the atom, there are protons, and the protons all have positive electric charge, and same sign electric charge repel. Now, there are many things about this iconic figure that are inaccurate, and one of those things is the scale. So if we scaled up a real atom to the size of this picture, that's about a meter, well, the size of the nucleus would then be about the size of a bacterium. So it's really cozy in there. The distance scale is around 10 to the minus 15 meters. So now you can go and use Coulomb's law to calculate the electric repulsion between two protons at a nuclear distance scale, and it produces an acceleration. Well, for comparison, the fastest roller coaster ride you'll ever take will subject you briefly to an acceleration of 6 g factors. G is the acceleration due to gravity on the surface of the Earth. A fighter pilot will briefly withstand an acceleration of 8 to 9 g factors wearing a special suit. So the acceleration produced by the electrical repulsion is about 10 to the 28th g factors. That is a big number. That's one of these Carl Sagan numbers. It's literally billions times billions times billions. So why doesn't the nucleus just blow apart? Because of the electrical repulsion between the protons. There has to be another force of nature. It's called the nuclear force, and now I hope you appreciate that it's also called the strong force. And the strong force is very subtle. It's been studied for decades, including up to the present day at the Large Hadron Collider at CERN. And thanks to these experiments and the brilliant insights of theoretical physicists, we now have a mathematical description of these forces of nature. So when you describe forces mathematically, there are two principles. One is that fields are created by charges, and the other is that fields move charges. So if we go back to the case of electricity and magnetism, here we have a plus and minus electric charge, and they create the kind of electric field that Graham was talking about, that Maxwell described. Now, the arrows here, what they tell you is the direction in which a test particle will initially move. And as you see, the direction changes as you go from point to point in space, and if they move in time. But there's also a magnitude of the electric field. It might be 5 volts per meter here and 3 volts per meter here. So what physicists do is they use equations to find the fields. That's the subject called field theory. And as Graham mentioned, the equations that describe the fields of electricity and magnetism are called Maxwell's equations. And you can find them on T-shirts. And it was a good day for James Clerk Maxwell when he added this last term to his equations, because he found that these equations have remarkable solutions. They have wave solutions, and when he computed the speed of the wave, he found that it was the speed of light. And thus he resolved the age-old puzzle of what is the nature of light. It's an electromagnetic wave. Now we can similarly describe the nuclear force. The proton is made of particles called quarks, and they create the strong force field. So here's a picture of the strong force field. But there's one very important difference with the strong force. So the magnitude of the electric force is a number, like 5 volts per meter. The magnitude of the nuclear force is a 3 by 3 array of numbers. And again, that 3 by 3 array of numbers changes as you move around in space and time. So these are called matrices, and numbers and matrices are very similar. For example, you can multiply numbers like 3 times 5 and get 15. You can also multiply matrices, And there's a rule. We don't have time to describe it, but there's a rule. But there's a very big difference also. You see, if you multiply two numbers like 3 and 5 and get 15, you could also multiply 5 times 3 and get 15. The same answer. But if you multiply matrices in the opposite order, you get a different number, a different matrix. So this is the difference between what's called commutative and non-commutative. And you're familiar with the difference between commutative and non-commutative operations in everyday life. When you got up in the morning, it didn't matter which order you put on your shirt or your pants. You could have put it on your shirt or your pants or your pants or your shirt. But now think about your underpants and your pants. Well, if you put on your pants first, well, that'll be a problem. Another place where we see non-commutative operations is in rotations in three-dimensional space. So you could rotate Graham's book around, or, well, we could take this tiger, and so this is the x-axis, and that's the z-axis. So if we first rotate around the x-axis and then the z-axis, that's one thing we could do. But we could also rotate around the z-axis and then the x-axis, and you see it's different. Okay, so this is this rotation. These rotations in three-dimensional space, this is part of the subject, the mathematical subject of symmetry. And it's called group theory. And the distinction between commutative and non-commutative groups is also called the distinction between abelian and non-abelian groups, and I'll use that language. So the theory of electricity and magnetism is using the groups which are abelian. So the groups go into the formulation of the field theory, and this is an abelian field theory, and the strong force is described by a non-abelian field theory. So the equations that govern the nuclear force field were first written at the Institute for Advanced Study in 1954 by Chen-Ning Yang and Robert Mills. And there's a great story about the first presentation of the Yang-Mills equations at the Institute. You can read about it in Graham's book. And they generalize Maxwell's equations. And yes, they have light-like solutions. We might call it non-commutative light. But they also have another kind of solution. So because of the non-abelian nature of these groups that go into formulating the theory, the equations, the Yang-Mills equations, are what are called nonlinear. Nonlinear equations have very interesting kinds of solutions. For example, Einstein's equations that govern the shape of space and time are nonlinear, and that's why there are things like black holes. More down to earth, equations that govern the motion of water are also nonlinear. In particular, the equations that govern water moving down a narrow canal are called the Korteweg-de Vries equations, and they have an interesting solution called a soliton. Now, this might not look too impressive, but let me stress here that there's no rocks, there's no lock or anything like here. This is a lump of water. Not only is it a lump of water, it's a lump of water which retains its shape as it moves down the canal. Now think for a second about how remarkable that is. Supposing you tried to make a lump of water in your swimming pool. What would you do? You would try to push together the water. Well, of course, it would just splish out the other way and flatten out. Suppose you tried to push a wave to the side of the swimming pool. Again, the water would dissipate. It would flatten out. It wouldn't retain its shape. This water retains its shape. In fact, what's being recreated here is the dramatic discovery of the soliton by a Scottish engineer, John Scott Russell, in 1834. He was riding by this canal. He saw this lump of water get created, and he was dumbfounded to see that it didn't dissipate. It just moved down the canal. And he chased it out to sea and spent the rest of his life studying this. Now, the Yang-Mills equations are nonlinear, and they have soliton-like solutions. And one of those soliton-like solutions is called an instanton. This is not an instanton. This is another lump of water, a soliton solution of water. And it's a very important distinction between instantons and solitons. You see, the lump of water is localized in the red direction, but delocalized in the blue direction. Also, it lasts for a long time. So it's delocalized in the time direction. It persists. Now, instantons are not like that. They're localized in space and time. Because they're localized in time, they're like flashes. They suddenly come on and then they go off. That's why they're called instantons. Okay, so they are localized in all 4 dimensions. They were discovered in 1975 by Belavin, Polyakov, Schwartz, and Tjupkin, and Sasha Polyakov is a professor here at Princeton University. So in the 1970s, the physicists were having a great time with these and other soliton solutions of these Yang-Mills equations. Now, meanwhile, back at the ranch, the mathematicians were beginning to take note. One of them was Michael Atiyah and his student Nigel Hitchen, and they were producing remarkable theorems about these instantons. And they had a student, Simon Donaldson, who said, let's count the number of ways of putting instantons into a 4-dimensional space. So instantons are localized objects in 4 dimensions, and the Yang-Mills equations are very fussy. You can only put the instantons into your 4-dimensional space in special ways. And the big surprise was, if you count the number of ways of putting instantons into this 4-dimensional space, you got a topological invariant. So here's a cartoon of the Donaldson invariants. I can't draw 4 dimensions for you, but let's imagine this as an analogy, this 3-dimensional space where we identify the opposite sides of the cube. And supposing we want to push 3 instantons into this cube. So we do that, and the Yang-Mills equations are very fussy, so maybe there's only one other way to do it. Then we would say that the Donaldson invariant for 3 instantons is 2. And now the surprising thing is that if we start scaling up the cube, excuse me, if we start scaling up the cube, then there will still be only 2 ways of putting those 3 instantons into the cube. And if you start deforming the cube to make a parallelepiped, again, there will only be 2 ways of putting the instantons in. So that's the topological invariant of a 4-dimensional space. And using this new topological invariant, Donaldson could prove dramatic new results. For example, there are exotic 4-dimensional spaces where you can't do calculus. Even the best mathematicians here at the Institute for Advanced Study can't do calculus on these manifolds, because it's logically impossible to do so. And for this and other remarkable results, Simon Donaldson shared the 1986 Fields Medal, and he shared it with Michael Friedman, who was simultaneously producing very deep results about the topology of 4-dimensional spaces. And in fact, this statement is really a synthesis of the ideas of Donaldson and Friedman. So all was sweetness and light, except that the Donaldson invariants are extremely hard to compute and interpret. Big fat books were written just to compute a few special cases. So mathematicians hit a wall. And when you hit a wall like that, that's an opportunity. So the turning point was when Michael Atiyah said, well, okay, you physicists gave us these instantons. What's the physical interpretation of these Donaldson invariants? And one physicist that listened was Edward Witten, and he went and thought about it. And his answer was, yes, Donaldson invariants can be computed within the framework of a Yang-Mills theory. Now, technically, it's not the actual Yang-Mills theory we use to describe the quarks and electrons that move in our world. It has a different set of quarks and electrons, and it has something called supersymmetry, but it's nevertheless a Yang-Mills theory. And so in the course of explaining that, he invented an idea called topological field theory, which was very important. So topological field theory is a vast simplification of physics. Length scales and time scales do not matter. There's no difference between yesterday, last week, 100 years ago, 1 billion years ago. There's no difference between your commute to work and your extragalactic vacation trip. But what does matter is topology. So you see, if you have 2 loops which are linked in 3-dimensional space, because distance doesn't matter, you can scale those loops up to be light years apart. So they're light years apart. They can't communicate, but they're still this topological invariant. There's this topologically non-trivial situation. And the field theory knows about it. So topological field theory has had a huge impact in both physics and mathematics. There are thousands of papers. It opened up fresh woods and pastures new. And it might even be of practical use. It's being used as a tool by Microsoft's Station Q as a potential road to quantum computation. That's another story for another time. So all was sweetness and light, except that Witten's answer was in the framework of quantum field theory. Computing the Donaldson invariants a la Witten requires computing probabilities in a Yang-Mills theory. How hard can that be? Well, in the abelian case, that's Maxwell's theory, it's hard, but it's solvable. That's the theory of quantum electrodynamics, which was completed by Feynman, Schwinger, and Tominaga. And there are very efficient ways for computing probabilities in this theory of this abelian field theory of Maxwell. In the non-abelian case, it's much to the nth power harder. It's not solved yet. Now recall that Witten reformulated the Donaldson invariants as probabilities for certain events in Yang-Mills theories in four-dimensional spaces. But computing probabilities in Yang-Mills theories is extremely difficult. So we seem to have exchanged one hard problem for another. Well, that creates an opportunity. The physicists had a trick called effective theories. So topology is unaffected by distance, by scaling things up. It's also true that in Yang-Mills theory, when one asks questions about events at larger and larger distance scales, the answers can simplify. In fact, the answers can be the same as answers to analogous questions in a different but simpler theory. So it's a little bit like pointillism in art. If you look closely at a pointillist painting, well, you can't quite see what's going on. But if you step back, if you take the longer viewpoint, then a picture emerges. So it's like that with effective theories. If you look at nuclear distance scales, at this theory of Witten and Donaldson and Atiyah, it's all very, very complicated. Incidentally, there's the Uhlenbeck compactification of the moduli space of instantons. It's all very, very complicated. So let's take the larger distance scale. Let's look at the distance scale of this room, 10 to 20 meters. Well, it's a blur. We don't see much. OK, let's go to much, much larger distances, something starting to resolve. We go to even further distances, and even further distances. And finally, a picture emerges, and what we get is a version of Maxwell's theory, not Yang and Mills's theory. So what's written here are what are called the Seiberg-Witten equations, after Seiberg and Witten, who prove that viewed from afar, the Yang-Mills theory used by Witten simplifies dramatically. It's an abelian field theory. It's a generalization of Maxwell's theory, not of Yang and Mills's theory, and therefore it's much easier to work with. Now, the Seiberg-Witten equations, they are also nonlinear, and so they also have soliton-like solutions. These are like vortices in a superconductor. And so remember again that you can measure topology by counting something. In 2 dimensions, we counted holes, we counted drains and spigots, and Donaldson counted the number of ways of putting instantons into a four-manifold. Well, you can also define new topological invariants called Seiberg-Witten invariants where you count these vortices. And just the way the drains and spigots were related to the number of holes, it turns out that the Donaldson invariants can be written in terms of the Seiberg-Witten invariants. They carry the same information about the four-dimensional space. So that's something that was conjectured by Edward Witten and was derived much more carefully in a paper I wrote with Edward. And I remember very clearly when Edward said to me, you know, Greg, we need to clear the air. People still don't quite believe this relationship. So we did that. We derived very carefully the relation between Donaldson invariants and Seiberg-Witten invariants, and nowadays it's a rigorous mathematical theorem. So the point is that these are much easier to compute. It's like trying to do a calculation with Charles Babbage's engine number 1 or with your laptop computer. So what was the response? This was a great breakthrough. The Seiberg-Witten invariants were much, much easier to compute. So this is a great breakthrough. So what was the response? Well, here there's an interesting cultural difference between physicists and mathematicians. So when a physicist has a good idea, a really good idea, then she or he will work feverishly over the weekend and get the paper out the next week. And okay, maybe maybe the logic is a little fuzzy from here, maybe there are a few mistakes, maybe the implications aren't quite thought out, but it's out there. It's part of the conversation. And so because it's part of the conversation, the physicist will rush in because all the simple and important calculations are on sale. Now, if a mathematician gets a really good idea, then she or he will think about it over the weekend and over the next week and over the next month and over the next year, and that mathematician will want to have all of the logical structure of the arguments just in the right order, and the implications are all thought out, so when the paper comes out, it's like a Greek temple. Okay, so that's actually not what happened with the discovery of the Seiberg-Witten invariants. There was a mad dash after this breakthrough, and Simon Donaldson wrote a masterful review of this episode, and I'll just read it from the beginning of his paper. He says, "In the last 3 months of 1994, a remarkable thing happened. This research area was turned on its head by the introduction of a new kind of differential geometric equation by Seiberg and Witten. In the space of a few weeks, long-standing problems were solved, new and unexpected results were found, along with simpler new proofs of existing ones, and new vistas for research opened up." So, let's wrap it up. So, I began with 2 basic questions in mathematics and physics, and I stressed that they didn't seem to have much to do with each other, but I hope you now appreciate that they're actually very deeply related to each other. Now, to my mind, this also helped settle a debate in the 90s. So physical mathematics is not without its critics from both the physics side and the mathematics side. And from the mathematics side, part of the concern is that physicists' techniques are very unrigorous. They often don't even bother with definitions, so what are they talking about? And these are legitimate concerns. And the most articulate elaboration of those concerns is in a paper by Arthur Jaffe and Frank Quinn, but the tone of the criticism is actually quite strident. And they use words like dangerous and unpleasant and destructive. And this instantly elicited a response from a large number of scientists. The leading article was by Michael Atiyah, and it's very cogent, very well reasoned. But to my mind, the best response of all was the discovery of the Seiberg-Witten invariants. So there's this remarkable story of back and forth, where the mathematicians start with a question, the shape of a space. The physicists started with a question, the strong force. So the mathematicians turn this into topological invariants. The physicists start talking about Yang-Mills instantons. And then you lob it to the other side, and now the mathematicians turn these Yang-Mills instantons into Donaldson invariants, and the physicists invent something called topological field theory. And that raises new interesting questions. If you lob back the topological field theory and the Donaldson invariants, well, you now want to compute those Donaldson invariants. So you need a long-distance effective theory that leads to the Seiberg-Witten theory. Lob it back, and presto, it becomes Seiberg-Witten invariants. So there's this remarkable back and forth, and this to me is emblematic of what I like to call physical mathematics. So you might be wondering, well, what about the future? This development was 25 years ago. Hasn't there been progress since then? Yes, there has been progress since then. This is just one vignette within the larger subject of physical mathematics. I could have told other stories, more recent stories, of remarkable interplay between mathematics and physics. You might still be wondering, well, what about four manifolds? And yes, there has been continued progress in four-manifolds. Physics has been used to derive new results about four-manifold topology. I've produced a few myself. There hasn't been anything like the Seiberg-Witten revolution, but there are questions which the Seiberg-Witten invariants cannot answer. And so this paper was written 12 years after the Seiberg-Witten invariants were discovered. So there are those of us who think that physical ideas will continue to lead to new insights and help answer some of these unknown questions about the shapes of four-dimensional spaces. And will that actually happen? Well, that's the nature of research. You're walking into the unknown. You have no idea. You only know it when you get there. So thanks for your attention. That's not all, but that's what we have time for.